My name is Caitlin, and I am a research associate for the Core Services of Glyconet, located in the chemistry department at the University of Alberta. Today, we're going to be talking about the 1D NMR analysis of carbohydrates. We can characterize simple carbohydrates using one-dimensional NMR spectroscopy. NMR spectroscopy is the most useful way to characterize simple carbohydrates because each NMR spectrum can provide valuable information that allows you to distinguish and identify protecting groups that are present, distinguish between the alpha and beta anomers, and help identify the monosaccharide that is present. It is essential to familiarize yourself with the important regions of the NMR spectrum for both the proton and carbon NMR. In the proton NMR spectra, the proton attached to the anomeric position will typically be observed around 4.5 to 5.6 parts per million, though they can sometimes be observed more downfield depending on the other substituents that are present. Importantly, the proton signal of the axial anomer will always appear more downfield than the proton signal of the corresponding equatorial anomer. This is due to the anomeric effect that is discussed in the introductory module. The remaining hydrogens that are part of the sugar backbone are typically observed between 3 and 5 parts per million. Specific protecting groups have characteristic chemical shift values as well. The benzyl, benzoyl, and benzylidine protecting groups all have characteristic aromatic chemical shifts of greater than 7 parts per million, whereas the methyl group of an acetyl protecting group is found around 2 parts per million. The isopropylidine groups are slightly more upfield at 1.5 parts per million, and a characteristic doublet with an integration of 3 can be found between 1.2 and 1.3 parts per million, which is indicative of a 6-deoxy sugar. In the carbon NMR spectra, the anomeric carbon is observed between 90 and 100 parts per million. In contrast to the proton NMR, if the sugar has an equatorial configuration, the signal for the carbon will be more downfield than if the sugar was in an axial configuration. This again is primarily due to the anomeric effect, which was discussed in the introductory module. The remaining carbons that are part of the carbohydrate skeleton are found between 60 and 80 parts per million, with the exception of carbohydrates that are N-acetylated. The carbon adjacent to the nitrogen is then found around 50 parts per million. Carbonyls that are present in benzoyl and acetyl protecting groups are found downfield around 160 to 180 parts per million, and the methyl of the acetyl and isopropylidine groups are found around 20 parts per million. Aromatic carbons are found in the typical range of 120 to 145 parts per million. If we look at the spectra of the monosaccharides shown on your right, we can see that we have 15 aromatic hydrogens between 7.2 and 7.4 parts per million, and corresponding aromatic carbon peaks around 120 to 140 parts per million. The proton attached to the anomeric carbon is the most downfield of the backbone hydrogens at approximately 5.6 parts per million, with a corresponding anomeric carbon peak found at just under 100 parts per million. The remaining backbone hydrogens are between 5.4 and 3.1 parts per million. However, if we look at the carbon NMR, we see that of the carbon peaks due to the carbohydrate skeleton, one is found at approximately 50 parts per million, which is indicative of a carbon that is adjacent to a nitrogen atom. The 4 methyl groups of the acetyl protecting groups are visible between 1.7 and 2.1 parts per million, and the corresponding carbon peaks are visible at approximately 170 and 20 parts per million. So now that we see how we can identify the protecting groups that are present, how would we distinguish whether or not this sugar is in the alpha or beta configuration? If we want to know whether or not we have the axial or equatorial anomer, we need to look at the coupling constants. Remember that the coupling constant is a measure of the interaction between neighboring hydrogens and that the value of the coupling constant is dependent on the strength of the interaction between the 2 neighboring hydrogens. The strength of the interaction can be predicted based on the torsional angle between 2 hydrogens of interest. This relationship between strength of interaction, or the coupling constant, and the torsional angle can be graphically shown by the Carpulus equation. When the torsional angle between 2 protons is 180 degrees, or the hydrogens are antiperiplanar to one another, we see very large coupling constants, typically between 8 and 15 Hz. As the angle between the hydrogens decreases to 90 degrees, the coupling constant also decreases. At 90 degrees, the coupling constant is at its lowest, between 0 and 2 Hz. Once the angle begins to get smaller than 90 degrees, the interactions begin to increase once again, resulting in larger coupling constants. When the hydrogens are gauche to one another, or the torsional angle is approximately 60 degrees, we see that the expected coupling constant is between 2 and 5 Hz. When the hydrogens are eclipsed or the torsional angle is 0, we have large coupling constants that are between 7 and 11 Hz. If we look at this in relation to sugars, we see that when we have two adjacent hydrogens that are in the axial position to one another, they will have very large coupling constants because the torsional angle between them is 180 degrees. However, if we have one hydrogen that is axial and one hydrogen that is equatorial, the torsional angle is approximately 60 degrees and the coupling constant will be between 2 and 5 Hz. Because of the chair conformation, even when both hydrogens are equatorial, the torsional angle is still approximately 60 degrees, so the coupling constant will also be between 2 and 5 Hz. If we go back and calculate the coupling constant in the signal produced by the proton at the anomeric carbon in the example on our left, we can determine which anomer is present. Recall that the coupling constant is determined by taking the difference of the chemical shift between the peaks within a signal and multiplying the difference by the strength of the magnetic field that the spectrum was run in. For our previous example, we are able to determine that the coupling constant is 8.4 Hz, which indicates that the protons at C1 and C2 are axial to one another, meaning that the orientation of the anomeric OH group is equatorial. Sometimes you won't know what the identity of your monosaccharide is prior to looking at the NMR spectrum. In the same way that we use coupling constants to distinguish the axial and equatorial anomers, coupling constants can also be used to identify the monosaccharide giving rise to your spectrum. This is done by looking at all the coupling constants within your spectrum and determining the relative configuration based on the size of the coupling constant. If we take the following example of a 1D proton NMR, we can quickly identify all the important peaks in the spectrum. We have our residual chloroform peak at 7.26 parts per million, as well as 5 acetyl groups around 2 parts per million. The remaining peaks are due to the backbone hydrogens. To figure out the relative configuration of all these hydrogens and thus the identity of the monosaccharide that is present, we must first calculate all the coupling constants. Once the coupling constants are determined, we can walk through the backbone by matching the coupling constants between adjacent hydrogens. If we start with the anomeric proton found at 5.68 parts per million, we can see that we have a doublet with a coupling constant of 8.4 Hz. The large coupling constant indicates that there is an axial-axial interaction between the anomeric proton and its neighboring proton in position 2, or the blue proton. To find the peak that is due to the blue proton, we simply look for a peak with a matching coupling constant to 8.4 Hz. We find the peak with a matching coupling constant at 5.3 parts per million and see that it is a doublet of doublets. We know that the coupling constant of 8.4 Hz is the interaction between the red and blue proton, and we can see that there is a second coupling constant of 10.5 Hz, indicating that the blue proton has a second axial-axial interaction with the green proton. To find the peak that is due to the green proton at position 3, we simply look for a matching coupling constant to 10.5 Hz, which we find at approximately 5.07 parts per million. Again, we see a doublet of doublets with one large coupling constant of 10.5 Hz, which we know is due to the interaction between the blue and green protons, and one smaller coupling constant of 3.5 Hz, indicating that the green proton also has an equatorial axial interaction with the gold proton. We continue along the backbone, identifying the peak that is due to the gold proton by matching the 3.5 Hz coupling constant, and find that the peak due to the gold proton is found at 5.4 parts per million. This doublet of doublets has two small coupling constants, one of which is the interaction between the green and gold protons, and the second of which indicates an additional axial equatorial relationship as indicated by the purple proton. To find the peak due to the purple proton, we look for a peak with a matching coupling constant of 1.4 Hz, which is found at 4.04 parts per million. This doublet of triplets has one small coupling constant of 1.4 Hz that is due to the interaction between the gold and purple protons, and a larger coupling constant of 6.3 Hz. With only the CH2 hydrogens at position C6 left, we know that the 6.3 coupling constant is the interaction between the purple proton and the pink protons. The peak due to the pink protons are both doublet of doublets. However, they are slanting towards one another due to their close chemical shift proximity. Sometimes this is called roofing or tenting of peaks. Each peak has one coupling constant of 6.3 Hz, which is representative of the interaction between the pink and purple protons, and one coupling constant of 11.2 Hz, which is representative of the geminal coupling between two pink protons on the same carbon. If we put all of this information together, we see that our unknown carbohydrate is the one shown on your right-hand side of the screen. So today we have seen how we can use chemical shift analysis to determine and identify what protecting groups are present, as well as we have seen how we can use coupling constants to distinguish between the axial and equatorial anomers, and how to use coupling constants to further identify unknown monosaccharides. The next time we will talk about how to determine the structure of more complex carbohydrates using two-dimensional NMR experiments.